Hello, this is Adjut team. In this video, we will present your autonomous navigation project developed during the last semester. These objectives of the project are used the location algorithms such as Book 0 and Book 2, along with odometry and Kalman filters to improve the accuracy in estimating robots' position and orientation. Additionally, we will integrate an Aruco detector which will allow use to obtain more precise location of the robot in the environment.
Odometry involves estimating the position and orientation of a differential robot based on wheel-encoded readings. For linear movement, the distance is determined by the number of wheel rotations and the wheel radius, while the speed is calculated from the rate of change of the distance traveled. For rotational movement, the angle is calculated by comparing the distances traveled by each wheel. Different distances indicate rotation. This method provides an estimate trajectory essential for autonomous navigation and integration with other positioning systems. Yet, since odometry relies solely on sensor readings, there is a big uncertainty built into the estimate.
Algorithm consists of the robot circumnavigating the obstacle and departing as soon as the robot can head towards the goal again. The robot initially moves in a straight line towards the goal. If an obstacle is encountered, the robot remembers the point of encounter, hit point, and starts to follow the contour of the obstacle. It continues to move around the obstacle until it finds a point where it can resume a direct path to the goal. The robot then leaves the obstacle and continues towards the goal. This process repeats until the robot successfully reaches its destination, ensuring efficient navigation in environments with obstacles. On the other hand, Book 2 consists of the robot circumnavigating the obstacle and departing immediately after finding a point that allows it to move towards the goal. Initially, the robot calculates a direct line from its starting position to the goal. As it moves along this line, if an obstacle is encountered, the robot records the location where the obstacle was first detected, known as the hit point. The robot then follows the contour of the obstacle, searching for a point on the obstacle's boundary that intersects with the start goal line, the leaf point. If this leaf point is closer to the goal than the hit point, the robot departs from the obstacle and continues towards to the goal. This process repeats until the robot successfully reaches its destination, ensuring efficient navigation despite encountering obstacles.
The Kalman filter is a tool that helps us predict and correct a linear model. But in this scenario, we have a two-plane situation where our model is not linear. It's actually it's a nonlinear model. Therefore, we correct it using an extended Kalman filter. This helps us to estimate the function using the angular velocities of the robot, therefore having an approximated mu. And with Arucos, we can measure the position relative to the Aruco and give it as a feedback to the Kalman filter and correct and give you a better estimate of mu. Same as mobile robot, the problem is that it still has an error, but it's way better because you can correct the covariance and have a better estimate.
We use the detection of Aruco makers through a camera to support positioning, which allow us to reduce our error by correcting the covariance matrix of our robot. Additionally, a Kalman filter was implemented to achieve this level of accuracy and correct errors, leading to better results in odometry.